Let's analyze the oscillation frequency of a double oscillator. Here we have a spring of length L, and it has a spring constant K, and there's two masses attached to the spring, one at each end. They can be unequal masses. So this, for example, could represent a diatomic molecule with an atom on each end. And we want to know if we compress the spring from a length of L to a small length of L, like this, and let it go, what's the oscillation frequency of block number 1 or mass number 1 and the oscillation frequency of mass number 2. Now, we know from video 7 that if we have a spring with a single mass attached to it, and if this is oscillating back and forth like this, it oscillates with a natural frequency that's equal to the square root of the spring constant divided by the mass. But here we have a single spring, and there are two masses attached to it. Now, in the last video, we discussed the motion of this system, and we determined the maximum velocity for mass 1 and mass 2. Now, how do we determine the natural frequency? And what we're going to do in this video is, well, there's two ways we can solve that. In this video, it's important to understand that when we compress the spring from each end, as we explained in the last video, we're doing it so that the amount of force that we're exerting on this one, on mass 1, going to the right, is equal to the amount of force that we're exerting on the other block, going to the left. So that means that as we're compressing the spring, we're not shifting it to the left or to the right. There's no translational movement. It also means that while we're compressing the spring, and when the spring shrinks down to a length of small l, the center of mass of the spring does not change position. So if this is the full length of the spring and the center of mass, say, is right here, then when we compress the spring, the center of mass is still right there. And realizing this is critical to the approach that we're going to use in this video for solving the natural frequency of the oscillation of mass 1 and mass 2. So before we do that, let's make certain that we are completely convinced that as we're compressing the spring, the center of mass does not change position. And let's just begin with a brief review of what we mean by the center of mass. So suppose we have two blocks and we have an origin here. Say this block of mass 4 is minus 5 units from the origin, and this block of mass 6 is plus 4 units from the origin. So the moment of this block would be minus 20, and the moment of this block would be plus 24. So our system has a net moment of plus 4. Now, if we combine the mass of these blocks into a single object, where would we place that single object so it would still have a net moment of plus 4? So the net moment is 4, and that's equal to the total mass times this distance from the origin, x bar. And clearly x bar is going to equal 4 divided by 10. So the center of mass, that is right here at plus 4/10. Now suppose then that we measure the distance of each object of mass 4 and mass 6, but now we measure their distance from the center of mass. So we could call this position vector 1 for this object, which points in this direction, and then we have a position vector for the second object that points in that direction. R1, that's going to be minus 5.4, and R2, that's now going to be 3 plus 3.6. So notice that with respect to the center of mass, the moment now is equal for each one of these. We have minus 5, or just 4, the mass, times minus 5.4. That should be 21.6. Then over here we have mass 6 times plus 3.6. That would be plus 21.6. So we notice that with respect to the center of mass, MR1 plus MR2 equals 0. And of course that's why at the center of mass we could balance the system right at this pivot point. Well, when we compress the springs, we're changing the position now of these masses, block 1 and block 2. So here, if we start changing their position, doesn't that mean that we would also change the position of the center of mass? Or could we do it in such a way that when this block moves to the left, say, that this block will move to the right a corresponding distance so that this equation is still valid? So for example, suppose we move this block from plus 4 to plus 3, and we move this block from minus 5 to minus 3.5 from the origin. Well, the distance now, R1 in this case, the distance from the center of mass, that would be minus 3.9. And here, R2, its distance from the center of mass, is plus 2.6. So if we take their moments, here we would have a mass of 4 times minus 3.9, that's minus 15.6. This would be 6 times 2.6, that's plus 15.6. So we move the blocks in such a way that this equation is still valid and the center of mass has not shifted position. Well, what happens then, let's say if we take the time derivative of this equation? So then we have m1 times dr1 dt. And of course, dr1 dt R1 is the position vector for mass 1. Well, that's just going to be the velocity of it. The rate of change of the position vector R1 is the velocity of that block. Likewise, the rate of change of the position vector R2, that's the velocity of this block. So, if we take the time derivative of this, we end up with this equation. And it says that the momentum of the system, the mass times the velocity, adds up to 0. So, what we see here is that if we move the blocks in such a way as to preserve the position of the center of mass, a consequence of that is the total momentum of the system adds up to 0. So each block has in magnitude, their momentum is the same, but of course they're opposite in sign because they're moving in opposite directions. Well, now going back to our problem, here we have the spring, and we have a mass at each end, and we said we're compressing the spring so that the force on this mass and the force on this mass, they're equal in magnitude, but they're opposite in direction. So if we added these two forces up, it add up to 0. So the net external force on the system is 0. And we know that when you have a mechanical system and the net external force applied to it is 0, the momentum doesn't change. Well, here the blocks are just sitting still. Then we started compressing them. So even though they're moving, and even after we release them, they're going to oscillate back and forth, the total momentum has to add up to 0, because that's what it was when we started. It was 0. And there's no net external force applied to this system. So we're saying that m1 v1 plus m2 v2 is 0. The total momentum adds up to 0. But as we just saw, that's exactly the condition that you need to preserve the position of the center of mass as you're moving the blocks together. That's what we just showed. We just demonstrated that right here. So, indeed, I think we could be convinced now that as we move the blocks together, the center of mass doesn't change position. As we're compressing it together and as they're oscillating back and forth, that center of mass sits right there. It does not change. So what we can do then is we can think of this single spring as being comprised of two smaller springs. With this spring, and we can say it has a length of R1 going from the center of mass to where the block is. Call this R1, and this mass is going back and forth on this spring that has length R1, and this block then is going back and forth on this spring, which will have a length, say, of R2. But remember, we just showed that mR1 plus m2 R2 equals 0. So from here we can say that the magnitude of R2, that will equal m1 divided by m2 times the magnitude of R1. So that's the length of this spring. This has a length of m1 divided by m2 times R1. So we're looking at our system now as not just a single spring that has a length of big L, and this single spring has a spring constant of K, but because the center of mass doesn't change position as these blocks oscillate back and forth, now we're thinking of it as two smaller springs, one with this length and one with this length, coupled together in series. And we can say, well, then this spring would have a spring constant, say, of K1, and this spring would have a spring constant, say, of K2. And the oscillation frequency of this mass, that would be, say, omega 1, that will equal the square root of K1 divided by M1. And likewise, this would be the square root of K2 divided by M2 for this oscillation frequency. But what are K1 and K2? Let's say from the original spring, we know its center of mass, we know its length, we know its spring constant, but what would be the spring constant for these shorter springs that we're trying to couple together in series? I think it was in video 9 we discussed coupled spring constants. And what we showed is that when we have springs coupled together in series, that the spring constant for the entire length of the spring, the reciprocal of that, equals the reciprocal of the spring constants for the shorter springs. And we proved this in video 9. And then in video 9, we also proved that K1, for example, that is equal to the length of the entire spring divided by the length of the shorter spring, which is R1, times the spring constant K for the entire spring. And again, we proved that in video number 9. So now we can say that omega 1, the square root of K1 divided by M1, that will be then just this divided by m1. So we have omega 1 equals square root of L over m1 r1 times k. So there then is the oscillation frequency of the first block. We know its mass, and if we know the position of this, if we know the center of mass of the spring, so that we know R1, and we know the spring constant for the entire spring, as well as its length, then we can calculate the oscillation frequency of the first block. So what about the second block? Then we need to determine K2. So likewise, K2, that equals the length of the entire spring, capital L, divided by the length of the smaller spring, and that's this. We have M1 times R1 divided by M2 times the spring constant for the entire spring. Or we can take this up into the numerator so K2 equals this, then of course omega 2, that's the square root of K2 divided by M2. Well, if we divide K2 by M2, we're just simply going to take this out of the numerator. So we can say that omega 2, that equals the square root of L divided by M1 R1 times K. And that's exactly what we obtain for the first block. So we're saying that they oscillate back and forth with the same natural frequency. And as we discussed in the last video, that's exactly what we would expect to happen, because our system is like this. Originally, the blocks are separated by a distance of capital L, then we compress it down to the smaller length, and we release them so the block 1 goes in this direction, the other block goes in the right direction, to the right, and then they keep moving apart until they're at a maximum separation distance, so the spring is elongated maximally. But of course that happens at the same time. Block 1 reaches its maximum displacement at the same time that block 2 reaches its maximum displacement. Then simultaneously they start to move together until the spring eventually is compressed to the smaller length L, and that happens at the same time. Spring 1 reaches its minimum displacement at the same time that spring 2 reaches its minimum displacement. Then again simultaneously they start to move apart again. So as we talked about in the previous video, we were certain that the frequency of oscillation of these two masses had to be the same, and indeed they are. We just proved that, plus we also derived an equation for them. Now M1R1, remember our equation, so the magnitude of M1R1, that's the same magnitude as M2R2. So if we want it over here, as we're talking about the second block, we could write in M2R2. These and these have the same magnitude, so it doesn't matter. But anyway, that is how then we determine the natural frequency of our double oscillator. And again, the whole thing was predicated upon realizing that as we compress the spring together and then release it and let these blocks oscillate back and forth, that the center of mass of the spring doesn't change position, so that we were considering our system then as two smaller springs coupled together in series. And then with that, from video 9, we had these equations, and we could use that knowledge then to solve for the oscillation frequency of both block 1 and block 2. What we're going to do in the next video is consider the same problem, that is, determine the oscillation frequency of these two blocks, only for that video we're going to use an entirely different approach. And again, just to remind you that the playlist for this series in analytical mechanics, it's at the website digital-university.org.